This lecture is an introduction to cointegration. So let's begin with the definition. This lecture will be limited to the case where we have two time series. So let's call them y1 through yt, that's my first process, and x1 through xt is my second process. These two processes may be co-integrated, and the requirements for them to be co-integrated are as follows. The first condition is that both of the processes must be I1. They must be integrated of order 1. Remember, that means that they are non-stationary, while when you do the first difference of them, they will be stationary. Here I have data on two variables, x and y, and these two series will be co-integrated. So first let's make a plot of both of them. You can do that by selecting both, go to View, Open Selected in one window, and open as a group. I will actually save this group for later, so let's just call it x and y. To plot this, just do View, Graph, click OK, and here's the graph. So there is a clear tendency for both of them to increase, so it seems reasonable that they are non-stationary. However, we also have a formal test. I can test for a unit root. So if I just open one of them, go to View, Unit Root Test, click OK, and we can see that the p-value is very large. We cannot reject the null of a unit root. However, if I look at the first differences, so if I do a unit root test in first differences, click OK, we can clearly reject that. It seems reasonable to conclude that this is an I1. In this particular case, I have simulated the data, so I actually know that both of them are I1. So that's the first condition. Here is the second and the important condition. There exists a parameter that we will call beta, such that yt minus beta times xt is stationary. This parameter beta is called the cointegrating parameter. In this particular data, I have simulated it such that x and y are indeed co-integrated with a co-integrating parameter of 1. And if beta is 1, it means that yt minus xt is stationary. So let's check if that's the case. So I just go to quick generate series and let's call it ymx for y minus x. So it's y minus x. If I open this, look at the difference, do a unit root test for this one, in level, we can clearly reject the null of a unit root. So the difference between y and x is actually stationary. So let me just quickly review this again. X and y separately are non-stationary. There is a tendency for both of them to increase over time. However, the difference between them is stationary. To explore this a little bit further, let's go back to the AR1 process, and we can actually analyze this without an intercept. So rho yt minus 1 plus epsilon t. Epsilon t is white noise, and since I don't have an intercept, the expected value for yt is 0. Now, if rho is less than 1, such that the process is stationary, then we will observe cycles in the data, but no matter what we look at the data, it will always cycle around 0. This is the mean reversion property of the process. There is a tendency for the process to revert to its mean, which is 0 in this case. Quite useful way to think about this is that there is sort of like a rubber band between the observations and the mean, which is 0 in this case. so that the data can actually travel away from zero, but the further away it travels from zero, the stronger this rubber band will pull it back towards zero. That is the case for the stable AR1 process. For the AR1 process where we have a unit root, rho equal to 1, there is no mean reversion. So if you like, the rubber band has sort of been cut. There is no tendency for this process to revert to zero. No matter how big yt is, it's just equally likely that it will go up as it will go down. So this idea translates to the cointegration case. In this case, the difference between these two series is stationary. So there is a mean reversion in the difference towards zero. Therefore, cointegration can be viewed as a rubber band between this series. They can deviate, and they do deviate, and they can deviate for many periods. But this rubber band tends to pull them back together. The further they are apart, the stronger is the pull. That's the idea behind cointegration. So to make a comparison, let's look at some data which is not cointegrated. Here is the data which is not cointegrated. You can see that both of them has an increasing trend, and indeed if you had performed a unit root test on this data, you would find that they are not stationary, but first differences are stationary, so they are both I1. However, in this case, the rubber band is missing. For example, right here, they start to deviate, but there is absolutely no tendency for a rubber band to have an effect here and pulling them back together. They are able to deviate from each other over a long period of time. In this case, I have actually simulated both of the time series as random walks with drift having no relationship with each other at all. Doing the same thing, calculating y minus x and performing a unit root test, I am not able to reject the unit root. So in this case, it seems like the difference is not stationary. So far, I have simplified matters quite a lot because in the simulation, I knew the value of the cointegrating parameter beta. That will in most cases not be the case. You only have your data for y and for x, not knowing the cointegrating parameter. So what you can do then is to simply estimate the cointegrating parameter. And we have the following result. If your data is cointegrated, if the y series and the x series is cointegrated, then you can actually estimate this beta parameter using OLS. So this was my data, which was cointegrated. I knew that my cointegrating parameter was 1, but we can actually estimate it. So just quick estimate equation, and all we have to do is YCM x. Here is my estimated cointegration parameter. Keep in mind that this only works if the time series are cointegrated. Notice something important here, because in general, we always avoid running OLS if your data is non-stationary. The argument was that there is a real chance that we will have a spurious result. If the data is non-stationary, if both are increasing over time, we will find a relationship between the two variables that actually doesn't exist. Here is an important exception to this rule. If your data is cointegrated, then you actually can run a linear regression using this non-stationary data. The estimated marginal effect is then the cointegration parameter. This cannot really be interpreted in the usual sense as a marginal effect, That is, we can't really say that when x increases by 1 unit, y increases by 1.02 unit. Rather, it's a long run relationship between x and y that we are considering. So if there is an increase in x of 1 unit, then y over the long run will increase by approximately 1.02 units. Going back to this case where we figured out that the x and y was not cointegrated, I no longer have a path of running a linear regression. In this case, the result will very likely be completely spurious. So if I run my regression ycx, I do find an incredibly strong relationship between x and y. The coefficient for x is hugely significant. R square is very large, and we may want to conclude that there is a strong relationship between x and y. I know that there is no relationship between them because these are just two completely independent random walks. We simply should not pay attention to any of the results in this regression, as we have found out that x and y are not co-integrated. So this is hugely important. If I have non-stationary data and that data is co-integrated, then yes, I can do the OLS regression and interpret the results. I don't have to worry about spurious regression in that case. If it's not co-integrated, then I should stay away from running a regression on this non-stationary data. So that seriously begs the question, how do we determine if two time series are co-integrated or not? Well, remember the definition. If I can calculate yt minus beta xt, then all I need is to check if this is stationary or not. The fact that I don't know beta is a nuisance, but I know that I can consistently estimate beta if they are co-integrated. So what we will do instead is to consider yt minus bxt, where b is the OLS estimator. So the process that we will carry out to test for cointegration is as follows. First, we have to argue that both of them are I1. Otherwise, the whole concept of cointegration is moot. The most common way of doing that is by doing the unit root tests. You should not be able to reject the null of a unit root in levels, but you should be able to reject the unit root in first differences. Then we run a regression of y on x. We typically include an intercept, and then we save the residuals. xt and yt are then co-integrated if these residuals are stationary. Unfortunately, it is not possible to do a unit root test on the residuals themselves. The technical details a little bit complicated, but it has to do with the fact that the residuals themselves are estimated, and that will actually invalidate the critical values from the augmented Dickey-Fuller test. So you actually need new critical values whenever you do a unit root test on residuals. To say this again, the critical values from the standard unit root test cannot be applied. You need special critical values whenever you do a residual based unit root test. But again, it's not something that we need to worry too much about because they are programmed into most econometric software. This way of carrying out a test for cointegration is often called an Engel-Granger test, and it's the most common test for cointegration for the setup considered in this lecture. So let's see how to carry out this test in practice. Let's do the cointegration test first for the data that actually is cointegrated to confirm that the test will give us this correct result. So the first step in eViews is to create this group containing your two variables. I can just open this group and then you just go to View, Cointegration Test, and it's a single equation cointegration test, and we use angle Granger. The rest of the information that you need to fill out is very similar to the information that you fill out for the augmented Dickey-Fuller test. Because remember, all we are doing is just doing a unit root test on the residuals. We're just adjusting the critical values. So we can do a maximum lag of maybe 12. We can include just a constant and then click OK. You have two rows. In the first row, X is the dependent variable. In the second row, Y is the dependent variable. So let's focus on this row. The p-value here is the important one. The null hypothesis is the same as in the unit root test. That is, the null hypothesis is that there is a unit root in the residuals. And a unit root in the residual means that the residuals are not stationary, and that in turn means that X and Y are not cointegrated. So that's the null. The p-value is very small, so this null should be rejected, and we can conclude that X and Y indeed are cointegrated. And a linear regression explaining Y with X is perfectly okay. Here is my other data set where X and Y are just two independent random walks with drift. They are not cointegrated, and let's see if eViews can detect that they are not cointegrated. So we do the same thing. We just open them as a group. We go to View, Cointegration, Single Equation, Angle Granger. Can keep everything as it is. And in this case, the p-value is very large, so we cannot reject the null that they are not cointegrated. Yes, a lot of double negations here. But the basic understanding is that this cannot be rejected, so it stands. And we have to accept or work under the assumption that they're not cointegrated. So no linear regression explaining Y with X in this case. Testing for cointegration in Gretel is just equally simple. In this case, I'm only doing it for one data set, the data set where they actually are cointegrated. Model, go to time series, and then you find the cointegration test here. The angle Granger is the one we want to do. Put the dependent variable first, like this. Gretel will also actually do the initial Dickey-Fuller test, just checking the first condition that these two are actually non-stationary. I know that they are non-stationary, so let's just skip that. Let's do the lag order of 0. We don't need any delta yt minus 1. And OK, and we are done. Here is step 1, just carrying out the actual regression. And in step 2, testing for a unit root in the residuals. Gretel, of course, knows that it's working with residuals, so it will adjust the critical value accordingly. The important part is this p-value, which again tells us there is no unit root in the residuals.